Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining about valence bond theory, which is helpful in understanding the structure as well as the geometry of coordination compounds. So let us start with understanding how it was proposed, who proposed it, as well as what is the basic idea about this valence bond theory. So it was proposed by Linus Pauling in the year 1931 in order to explain the properties of these coordination compounds. And of course, he was awarded with the Nobel Prize in 1954 for this wonderful the theory which was put forwarded by him. Now, according to this theory, so already we have been discussing about coordination compounds from the last 2-3 videos. I have explained about that, about the nomenclature as well as what are coordination compounds, how are these bonds formed. So all these details have already been explained. If you have not watched those videos, you can go to the profile and you can watch all these videos. And even I'll be providing the links to these videos in the description box. So now let us try to understand how do we predict the geometry of these coordination compounds with the help of valence bond theory. Now, according to this theory, a coordinate bond is formed by the overlapping of the orbitals. So which orbitals? One is the orbitals of the ligand as well as the orbitals of the metal. So of course, we know that in the coordination compounds, there is a central metal atom or a central metal ion, which are the metal is forming the bond with the ligands, right? So this we are already aware about. So now let us try to understand how this coordination bond is formed between the metal and the ligands. So mainly we know that ligands, at least they should contain a pair of electrons, so that these pair of electrons are used to form the coordinate bond. So here you can see the orbital of the ligand. You can see there is a pair of electrons. So at least there should be one pair of electrons on the ligand, and the metal orbital should be vacant, so that a coordinate bond should be. So for the coordinate bond to be formed, these are the two main conditions. Okay, so the metal orbital should be vacant, as well as this vacant orbital has to overlap with the ligand orbital, and the ligand orbital should at least have, so one ligand should at least have one lone pair of electron. So here, when one coordinate bond is formed, one ligand orbital has two electrons, and the metal vacant orbital will undergo overlapping. Now, let us try to understand the features, the silent features of this valence bond theory, and then let us look into the examples to understand it better. So now, here we know that of course the metal atom or the ion, it should have a certain number of orbitals which is equal to the coordination number. So that many vacant orbitals will be there, and these vacant orbitals will be filled by the electrons of the ligand, because the ligand is using its electrons to form the coordinate bond with the metal. Now, the metal ion uses hybrid orbitals. So, of course, it's not just the orbital of the metal. First of all, the orbitals will undergo hybridization. So, you might have already studied about hybridization, sp3, sp2. So many different types of hybridization are there. So, here, the hybrid orbitals of the metals are involved in overlapping with the orbitals of the ligand. Now, the ligands, of course, they should have at least one orbital which contain a lone pair of electrons. Only then we call them as ligands, right? Now, the vacant orbital of the metal as well as the ligand orbital, which already has a pair of electrons, these both will overlap with one another to form the metal ligand bond. So we have to always represent it this way, because the electrons are moving from the ligand to the metal. It's not exactly moving, but the electrons are used from the ligand to form the bond with the metal, to form the coordinate bond with the metal. It's not just a covalent bond, it's a coordinate bond. So that's why you have to indicate it with the help of an arrow. Right. Now, the d orbitals which are used in hybridization can be either outer d orbitals, which we call it as outer nd orbitals, or the inner orbitals, which are represented as n-1 d orbitals. Now, for example, if I take the outer d orbitals as let us say it is 3d orbitals, or if I tell 4d orbitals, if n is equal to 4, then n minus d orbital will be the inner one. Okay, so that way we are going to understand nd and n minus 1d, so inner or outer complexes. If there are any unpaired electrons, once the bonding is over, once the complex is formed, even after that, if there is any unpaired electron that is present, then the complex will be paramagnetic in nature. So it will have the magnetic property. If there are no unpaired electrons, of course, it is not magnetic. Okay, it is diamagnetic in nature. So that is how we differentiate diamagnetic as well as paramagnetic property of the coordination compounds. Now, if there are unpaired electrons, then we can find out the magnetic property by this particular formula. Mu is equal to the square root of n into n plus 2, where n is the number of unpaired electrons. So, of course, if there are unpaired electrons, let us say one unpaired electron, then you have to substitute this n is equal to 1 in this formula to find out the magnetic moment. Now, if there is any strong ligand, for example, cyanoligand, Cn minus. Okay, so this is a strong ligand. Carbonyl ligand, CO, it is a strong ligand. So suppose if there is any strong ligand that is present in the complex, then there is a possibility that the unpaired electrons will be forced to pair up with each other. So there will be pairing up of electrons, forcible pairing up of electrons against the Hundstone whenever there are the strong ligands. So we'll be talking about strong field ligands, weak field ligands in much detail in my next video about crystal field theory. But for now, you can just keep it in mind that there are certain ligands which are strong in nature. They are called as strong field ligands. There are certain ligands which are called as weak field ligands. Only in the presence of strong field ligands, there will be pairing of electrons, the forcible pairing of electrons, which is against the Hund's rule. Now, let us talk about a few examples to understand this valence bond theory in detail. So first of all, we are talking about the octahedral complexes. So in octahedral complexes, mainly there are two types, inner orbital complexes as well as outer orbital complexes. Now, let me talk about a simple example. Okay, FeCN6, and we have here 4 minus charge. Okay, so first of all, you have to calculate the oxidation number of the central metal ion. Okay, so of course we know it is ferrocyanide ion. Okay, so let us try to calculate the oxidation number. So take it as X for the coordination number of, the oxidation number of Fe. And then cyano, we know that it is -1 charge. There are 6 cyano ligands, so -1 into 6. Okay, and the total charge here you can see it is -4. So x minus 6 is equal to -4, or x is equal to -4 plus 6, which is equal to x is equal to +2. So the oxidation state of ion in this particular ion, complex ion, is +2 charge. Okay, so now iron, we know that atomic number is 26. If I have to write the electronic configuration, we can write it as argon. Argon, we know that atomic number is 18. Okay, then we have 3D, 4S, 4P. Okay, 1 second. Okay. Yeah, 4S and 4P and so on. Okay, you can also write 4S in the beginning because we know that 4S has lower energy when compared to 3D. But now, just for convenience, let me write 3D in the beginning and then 4S and 4P and so on. Okay, so in argon, we know that it is atomic number 18. So let us just leave about these 18 electrons. After 18, of course, we have to reach till 26 now. So we know that after this, out of 3D, 4S, and 4P, the next subshell to be filled is 4S, right? Because it has lower energy. So let me put 2 electrons here, because in S subshell, there are 2 electrons that can be filled. So now 20 is done. 6 are remaining. So of course, in the D subshell, we can fill 10 electrons. So remaining 6 will be in the 3D orbitals. Okay, so this is how we fill. And so now we are not concerned about 4p orbital for now. So this is iron in the ground state. Now we know that in this complex, iron is in the +2 state, right? In the oxidation state is +2. So Fe2 plus. So how do we write the electronic configuration? So argon, now we have here, so we know that it is in the +2 state. So of course, these 2 electrons will be removed off, because whenever it is in the +1, +2 state, on the positive oxidation state is there, it is because of the loss of electrons. So these 2 electrons have been lost from the iron atom, so that now the configuration is argon with the 3d6, 4s0. Okay, now let me write it in the expanded state. So argon 3d6. So let me write it like this. Okay, 4s0. So here 3d6. So we know that whenever we are filling 6 electrons, first all the subshells have to be filled like this. And now I can pair it like this. Right. So we have 3d6 and 4s0. Now, let us talk about the ligand that is present. So we know that the ligand that is present here is cyano. So I already explained that the cyanoligand is a strong field ligand. So now what does this cyanoligand do? So whenever a ligand is a strong field ligand, it will force the pairing of electrons. Right. So this is 3d and this is 4s. Now, if the electrons are forced to pair up, what will happen? So we get it like this. So argon 2, 3, 4, 5. Okay, now this is already paired. Now there are 4 electrons. So these 4 electrons will be paired in this way. Okay, because of the presence of the ligands. This is in the presence of the ligands. That is FeCN6 4 minus. Okay, now you can see that next is 4s is this is 3d, this is 4s. So next orbital, next subshell is 4p, right? So now we know that there are 6 cyanoligands. Each cyanoligand will give 2 electrons, right? It is a unidentate ligand, so of course it has 2 electrons which can be used to form the coordinate bond. So there are 6 cyanoligands, so each ligand gives 2 electrons, so totally 12 electrons are accepted by the metal in order to form the coordination compound, of course. So now the incoming 12 electrons should have 6 orbitals, right? So that the 2 electrons can be filled in each of these orbitals. So now we can see here that in the presence of cyano ligands, the 6 cyano ligands, so 12 electrons are accepted by the metal. So let me just show it in some other color so that it is easy for you to understand. So here, these are the electrons accepted from the ligand. Okay, there are 6 cyano ligands. So totally 12 electrons are accepted by the metal from the ligands. So this is how it takes place. Now you can see here, 2d orbitals, 1s orbital and 3p orbital. So of course, the hybridization that has taken place in the metal, so that the hybrid orbitals are overlapping with the orbitals of the ligands to form this complex. So that is nothing but D2, see here, this 2D, and then we have yes, and here we have P3. D2 sp3. Okay, D2 sp3 hybridization is taking place here. Now, let us talk about this particular thing, inner orbital complex or low spin complexes. So this is what we are going to understand in detail now. Okay. Now, when I'm talking about inner orbital complex, that is nothing but where there is n minus 1 d orbitals that are involved. Now, look at the outer orbital that is present, that is 4p, right? Now, what is the value of n here? It is 4. Now, in the hybridization, which d orbitals are involved? It is the 3d orbitals that are involved. So, n minus 1. So that's why we call this complex as the inner orbital complex. Now, about low spin and high spin, let me give a brief idea. You'll be understanding more about this when I explain crystal field theory. But for now, you can just understand that whenever there are less number of unpaired electrons that are present in a particular complex, you call it as low spin complexes. Okay, so here, of course, there are no unpaired electrons at all. So, of course, it is a low spin complex. Now, talking about geometry. So, of course, there are 6 ligands which are present here in this complex. So geometry is octahedral. Okay, so ion will be in middle, and then we have the cyano ligands which are forming the bonds like this, the coordination bonds. Okay, and minus 4 charge. Okay, these 4 ligands will be in one plane, the 4 cyano-ligands, and these 2 ligands, one will be above the plane and one will be below the plane. Okay, so the geometry is octahedral. Magnetic property, of course, here there are no unpaired electrons, so the magnetic property is diamagnetic in nature. And the type of complex is inner orbital complex. Of course, n minus 1 d orbitals are involved here, so it is an inner orbital complex. Let us talk about the other type of octahedral complex, that is outer orbital complex or high spin complexes. So let us take the example of COF6 3 minus. So first let us look into the oxidation state of cobalt here. So take it as X, F, the fluoride, fluoro ligand is F minus. So there are 6 here. So minus 1 into 6 is equal to minus 3. So X minus 6 is equal to minus 3 or X is equal to plus 3. So cobalt is in the plus 3 state. So cobalt. So cobalt, we know atomic number is 27. So let me write the electronic configuration. So argon, 3d, 4s, and 4p. So here argon already 18 electrons are filled. So 2 electrons, let me put it in the 4s orbital. So 20 are done. So 7 are present in the 3d orbitals. Okay. Now it is in the plus 3 state. So of course 3 electrons have to be removed when I write the configuration for CO3 plus. So argon 18. So 3 electrons if I remove. So first of all, the 2 electrons from 4s will be removed and 1 electron from here. Okay, so 3d6, 4s 0, and of course 4p 0, of course. Okay, now let me write it in the expanded form. Argon 18. So 3d6 electrons. So 1, 2, 3, 4, 5, and 6. Okay. Now, let us talk about the ligand, the fluoroligand. The fluoroligand is a weak field ligand. Okay. So whenever the ligand is weak field ligand, it cannot forcibly pair the electrons in the metal. Okay. Now, if the electrons are not paired, so this is the 3D, right? This is 3D. Next we have 4s, then we have 4p and so on. Then we also have 4d and so on. Okay. Now, if there is no pairing of electrons, forcible pairing of electrons, then what will happen? Which orbitals will be involved in bonding? Of course, these orbitals. Okay. We have 4d here. Okay. So these orbitals will be involved in bonding with the ligand. Okay, because here there cannot be pairing, the forcible pairing of electrons. So if there are no vacant orbitals, then how can the electrons from the ligand come? Right, each ligand will have 2 electrons which will be used to form the coordinate bond. So each 2 electrons will require 1 vacant orbital. Right, so if there are 6 fluoroligands, so of course there should be 6 vacant orbitals. So of course here there are no vacant orbitals now because there is no pairing of electrons. So we start with 4s, 1, 2, 3, 4, 5 and 6. Okay, because there are 6 fluoroligands, so of course they require 6 vacant orbitals. Okay, so now you can see that in the presence of the fluoroligands, okay, so we get argon. Then we have these electrons which are not forcibly paired. So it will be as such. Then we have the 4s, 4p. Then we have the 4d. Now there should be 6 vacant orbitals. 1, 2, 3, 4, 5, 6. Okay, these orbitals. So there will be what type of hybridization is taking place here. So there is yes, there are 3 p orbitals, so sp3 and d2. So here the hybridization is sp3 d2 hybridization. Okay. Now, of course, the electrons from the ligands. Okay, let me show it in another color. Okay, so it will be filled here. Okay, these are the electrons of the fluoroligands. Okay, I hope it is clear. So it is sp3d2 hybridization. Now, the outermost shell, you can see the outermost orbital. that is involved in the bonding, it is 4d. So n value is 4 here. And of course, the d orbitals that are involved here is also 4d, nd orbitals. So here there is nd orbitals which are involved in the hybridization. So of course, this particular complex is an example for outer orbital complex. And of course, you can see here in the complex there are 4 unpaired electrons. Right. So I told you when there are unpaired electrons, of course, they are called as high spin complexes. So this is a high spin complex. And of course, it is an outer orbital complex. Geometry is, of course, it is again octahedral, because here you can see cobalt is in the middle. So fluoro ligands will be here. Okay. The total charge is 3 minus. So these 4 fluoroligands will be in one plane. This fluoroligand will be above the plane, and this fluoroligand will be below the plane of in this particular arrangement of atoms. Okay. Magnetic property, of course, it is paramagnetic because there are 4 unpaired electrons. Type of complex, of course, we already know it is an outer orbital complex. Next, let me just quickly explain about tetrahedral complexes and square planar complexes and how they are formed. By now, I think it is very easy for you to pick up and write the structures just by looking into the formula of the coordination compounds. So let us talk about nickel tetracarbonyl. So nickel tetracarbonyl. So carbonyl ligand is a neutral ligand. So here we can see that X plus 0 is equal to 0 it will be, because there is no charge as such. So nickel oxidation state is 0 here. Okay. So nickel atomic number is 28. Okay. So we write the electronic configuration. Argon. Okay. And then we have the 3D 4s. So 2 electrons, let me put it in 4s here. So 20 are done, 8 in the 3D orbitals. Okay. Now, of course, it is not in the +1 or +2 state. The oxidation state is 0. So there is no loss of electrons. So let me write the the electronic configuration in the expanded form like this. So there are the 4s2, 2 electrons will be here, and 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is 3D and this is 4s. Now let us look into this carbonyl ligand, CO ligand. It is a strong field ligand. Okay, 1 second. Okay, it is a strong field ligand. So whenever it is a strong field ligand, of course, we know there is forcible pairing of electrons. So now in the presence of the ligand, okay, there will be pairing of electrons now, since it is a strong field ligand. So there are 8 electrons here. So 1, 2, 3, 4, 5, 6, 7, 8. Now there are 2 electrons here in the 4s shell that also will be pushed and it will be forced to pair, so that all these 2 electrons also will move to the 3D subshell. Okay. Now we know that there are 4 CO ligands. So of course 4 vacant orbitals are required, so that 2 electrons from each carbonyl ligand can fill into these vacant orbitals. So which are the outer orbitals now? Next is 4s, and then we have the 4p. Right? So now there are 4 CO ligands. So 2 electrons from each CO ligand will be filled in these vacant orbitals. Okay, so you can see the hybridization now. Here there is one s orbital. Here there are 3 p orbitals. So sp3 hybridization. Okay, whenever there is sp3 hybridization, we know that the geometry is tetrahedral. Right, so tetrahedral geometry. So how will be the arrangement? So nickel will be in the middle. So carbonyl group like this. Here there is one more carbonyl group and carbonyl group. So this is the structure of the tetrahedral complex. Okay. So geometry is tetrahedral. Magnetic property, of course, there is no unpaired electron. So the complex is diamagnetic in nature. Type of complex, of course, it is a tetrahedral complex. So here there is no d orbital that is involved. So we cannot talk about inner or outer complexes because it is just the sp3 hybridization. So this is how the tetrahedral complex is formed. Let us go to the last one. So how these square planar complexes are formed. So let us take the example of cupramonium sulfate complex. So sulfate ions are not shown here. So of course, the only the complex ion is shown here. So NH3 is a neutral ligand. So let me take X here. NH3 neutral ligand. So 0 is equal to +2 charge on the complex. So X is equal to +2. The oxidation state is +2 here for copper. So copper atomic number is 29. Right. So it is in the +2 state. So first let me write the electronic configuration for copper. So argon, then we have the 3d 4s. So 2 electrons here. There's 18 electrons in argon. So 20. So 9 here in the 3d orbitals. Correct. Now let us talk about the Cu2 plus. Okay. So Cu2 plus we have argon. Okay, so 2 plus means 2 electrons from the 4s is lost. So there are only 9 electrons in this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is how it is happening. Okay, now we are talking about again NH3. There are 4 ligands that are there, and now we have to remember about the square planar complex. One important thing. So whenever there is the formation of square planar complex, the hybridization that is involved is dsp2 hybridization. That is first one vacant orbital from D, and then one vacant orbital from S, and two vacant orbitals from P orbitals. Okay, so now there is one electron here in the d orbital. Now, what is happening in the presence of this amine ligands or ammonia? So we call them as amine ligands, of course. Now, this one electron, so of course, this is 3D. Next, we have 4s, and then we have 4p, right? Right? Now, this ammonia ligands, there are 4 in number. So they want 4 vacant orbitals. Now, if there are 4 vacant orbitals, now first of all, when we are talking about the structure of this particular complex, it is square planar in nature. The structure has already been found out. But how do you explain this structure? Because if you take these 4 as the vacant orbitals, then it will be sp3 hybridization, then it will be tetrahedral, right? We know that it is not tetrahedral in structure. Now, how do you account that this particular structure is the square planar structure? So now what happens is, in the presence of the ligand, in the presence of ammonia ligand, this one electron will be shifted to the 4p orbital, so that this orbital is available for taking up the electrons from the ligand. Okay, now what will happen in the presence of the ligands? Okay, so we have argon, 2, 3, 4, 5. So already these electrons are paired. So whatever the one electron was present here, that is shifted to the 4p orbital. So we have that electron shifted here. So we can see that there are 4 vacant orbitals that are available here. Okay. Now you can see here, this is 3d, this is 4s, this is 4p. Now one d orbital, one s orbital, and 2 p orbitals. So dsp2 hybridization. So of course here now the electrons from the ligand will come and occupy the vacant orbitals, because there are 4 ligands, so 8 electrons totally. So those 8 electrons will occupy these vacant orbitals. Okay, so now of course we know dsp2. So whenever there is dsp2 hybridization, it is a square planar complex. So square planar complex means copper here and 4 ammonia ligands will be in the same plane. Okay, same plane as that of copper. So this is the square planar complex. Okay, so geometry is square planar, and of course the magnetic property, by now I hope you all are expert in guessing and analyzing the magnetic property. So of course there is a one unpaired electron here, so of course it is paramagnetic in nature. Okay, so I hope now it is clear how to predict the structures, how to explain the structures of the various coordination compounds by making use of valence bond theory. Of course, there are a few limitations with respect to valence bond theory. And because of these limitations, it was crystal field theory, which was then put forwarded so that it could explain so many different properties as well as so many different concepts which couldn't be explained by valence bond theory. So what are those limitations? So it does not explain the spectra of coordination compounds. Okay, so about spectra of coordination compounds, again, I have done a video, I have explained about it, so you can just watch it to understand in detail. Okay, and this valence bond theory does not give a quantitative explanation about the magnetic data, and it cannot explain about the stability of the compound. So which compounds are stable, which are less stable, all this cannot be explained. And it cannot explain, even though the coordination number is 4 in certain complexes, as we have seen in the previous cases, why some complexes are tetrahedral and why certain complexes are square planar. So that cannot be explained by the help of valence bond theory. Okay, so these were the limitations, so which were then overcome by putting forward the crystal field theory. So let us try to understand about crystal field theory in detail. In my next video, I'll be explaining about it. So until then, thank you for watching the video. I hope the concept is clear. So